Okay, so let's start. Again, we want to finish chapter 1, and let me, where is it? Okay, so hopefully today we can finish all of these points. And there is one thing, if you remember the previous lecture, we explained the types of work. So we said we have work of expansion, contraction, we have flow work, we have shaft work. So this is the original equation of work. Work is force times distance. And this lecture just gave you a summary of all the math we developed in the previous lecture. I just combined all the slides in one of them. Please take a picture of this one. This is not part of the slides. I just did it yesterday. So if you need like this summary of equations, you'll find it. Okay. So we have here the three final forms of energy we have. So we have this one. This is the formula that we can use to calculate work of expansion contraction. This is the formula that we are using to calculate the flow work, and this is the formula we are using to calculate the shaft work.
I just have a question about the quizzes, because I thought last time you said we didn't get contact for quiz 2, and then the date was changed to the 12th, but then quiz 3 is on the 8th, on Tuesdays.
Okay, remind me after the lecture. I will check it when I finish, okay? Okay. This is the example that we didn't solve in the previous lecture, so we can start with it today. So we have pipe, or we have pure water. This pure water flows through a horizontal section of a pipe. The length of this pipe is 5 feet and 1 inch in diameter. So now we have length in feet, length of inch. So if we need to use these dimensions, so we need to convert the units because these units doesn't match. Water entering the pipe has flow rate 100 kilogram per minute with temperature 100 degrees Celsius, pressure 2 bar. The exiting water has flow rate 100 kilogram per minute, so the same mass flow rate through the pipe. Temperature 100 degrees Celsius, same temperature as well. And the pressure, we have pressure change. The pressure at the outlet is 1.95 bar, so we have delta P happening through the fluid is moving in the pipe. Density of water is 961.5 kilogram per meter cube. Determine the rate at which work is done at the pipe entrance, at the pipe exit. So the first thing, this shape or this one, do you think this is work of expansion contraction or flow work or shaft work? Which one of the three? Flow work. Okay. There is no, like piston, we have expansion contraction. There is no any rotatory part, so this is a flow work. And again, from the previous slide, the flow work, its equation is P times the volumetric flow rate, or pressure times the volumetric flow rate times specific volume. Specific volume, this is the reciprocal of density. So basically, to solve this one, so what we have this is type of flow work. And flow work, we have it to be pressure times volumetric flow rate, which is pressure times mass flow rate times specific volume, or pressure times mass flow rate times 1 over density. So the specific volume is the reciprocal of density. So this is the equation we have for the flow work. Let's start at the entrance. The pressure at the entrance, we have it given 2 bar. Mass flow rate at the entrance, so this one is 100 kilogram per minute. We have density at the entrance, 961.5 kilogram per meter cube. And again, let's say at the exit, also we have pressure is 1.95 bar. Mass flow rate will be the same, 100 kilogram per minute. Density does not change, 961.5 kilogram per meter cube. This is all the information that we need to substitute in the equation. But here you can see that mass flow rate in the SI system density, also in SI system, and the pressure is bar. So bar, is it the unit that we are using to express pressure in SI system? What are the pressure units in SI system again?
Pascal.
Pascal. So we need to convert this part to Pascal. So this one will be 2 times 10 to the power 5 Pascal. This one will be 1.95 times 10 to the power 5 Pascal. And then substitute in the equation. So we have the rate of work. This one will be 2 10 to the power 5 times 100 times 961.5 kilogram per meter cube. Kilogram per meter cube. So just if you substitute this one here, so this one will be 20800 joule per minute. So this will be the rate of work at the inlet. And again, at the other side, for the outlet, just substitute the numbers. We have 1.25 times 10 to the power 5 times 100 times 961.5 kilogram per meter cube. Again, when you substitute this will be 20300 joule per minute. Just put the numbers, and this will be the answer we have.
I thought it was supposed to be 1 over the density.
Okay, sorry. Yeah, this is correct. Yep. So this one divided by 961.5 divided by 961.5. Okay. Okay. So here now we calculate rate of work at the inlet, rate of work at the outlet, but both of them have the same sign. And here this doesn't match because let's see, this is the inlet, and as we said, what will be the pressure? So the pressure, this is the normal force, normal to this cross-sectional area. So this will be the work or the direction of pressure we have at the inlet. And for the outlet, let's put it here, for the outlet, so if this is the cross-section of the outlet, the pressure direction will be here. So if you have the inlet rate and the outlet rate with the same sign, so this means the pressure effect in the same direction. And this doesn't match because pressure, it's normal to the area. So we have here the inlet, the pressure direction is from left to right, here the pressure direction is from right to left. So how we account for this? If we are assuming the flow is moving in this direction, so let's assume this is the positive sign we have. So at the inlet, the pressure force in the same direction of the flow, which we are assuming this is the positive sign, so at the end, the pressure should be positive and this one should be positive. But here at the outlet, the pressure direction is opposite to the flow direction, okay? So how we can express this difference in the direction? Just by adding a negative sign here at the outlet. So this negative sign here, so this will indicate that the pressure direction applied pressure direction at the outlet is opposite to the flow direction. So by adding this negative sign, then the answer is complete. Clear this part? Any questions? Okay. So this was the example we missed last time, and then we're gonna continue the forms of energy. So now we are done with the static forms of energy, which is heat and work. Then the other category is, we are done with the dynamic forces of energy. Now we have the static forces of energy. These are the energy that is stored inside the system, and we have three types of them: kinetic, potential, internal energy. Kinetic and potential, this is something you are familiar with. Kinetic energy, this is the amount of energy the system has because of its motion relative to a reference. And how we can calculate it from this equation. Kinetic energy is half mass of the system times velocity square of the system. Potential energy, the type of energy the system has because of its elevation or position relative to a gravitational field. And how we can calculate it? Potential energy, mass of the body, times the gravitational force, times the height, the distance that's or the position of this body. The value of gravity, you know this number. So this is how we can substitute G in the SI system. But if your problem in the American system, so this is the value that you need to substitute with. Okay. We know that the potential energy again it's affected by the height. So if you have body and this body resting at the F level or C level, whatever you reference, so Z or H is 0, so the potential will be like 0. But as you are increasing the height, going up, H or Z increase, so the potential energy is increased. If you have a body and this body or system is not moving, so the velocity is 0, so the kinetic energy is 0. This body start to move, then it start to gain kinetic energy. And by increasing velocity, the amount of kinetic energy of this body increase. So these are the two factors affecting it, besides for sure the mass of the system or of the body we have. Now let's see this example. We have an object. This object is dropped from a height of 50 meters. So we have an object. This object at height 50 meters, it's fixed at this height, and then we allowed it to drop. So initially, when the system at this 50 meters, it was like fixed. There is no velocity for this body. Just we are resting it or we are keeping it at this distance, 50 feet. And then we allow it to fall, so it start to fall until it reach the ground, for example. Okay. We have no forces affecting on this object other than gravity. So only this body is moving under the effect of gravity. What is the velocity it have when it hits the ground? What will be the final value of the velocity here when it hits the ground? So basically, you have body. This body is not moving, but it has or we are keeping it on a certain elevation. It's not moving, so this body initially doesn't have kinetic energy. What it has? Only potential energy, because you are keeping it at 50 feet above the ground. Then you allowed it to move. So its position start to decrease or the height decrease, so it's losing the potential energy. But since energy is conservative property, which is the second law of thermodynamics, which we will start to mention in this lecture, it's losing the potential energy. So this energy loss should appear in another form. So what is happening? This body starts to gain velocity. So the potential energy this system is losing, it will appear in the other form, which is kinetic energy because of the movement. So any potential energy lost will be accepted or gained in the form or converted in the form of kinetic energy. So basically here we have body at the initial position. This system has kinetic energy equal to 0 because it's not moving. But it has a potential energy which we can calculate from this equation, mgh. Then final state, when it hits the ground, this body has kinetic energy, not 0, because now it's moving, so it has a kinetic energy value. And we can calculate it, the kinetic energy, from the equation half mv squared. But finally, when it hits the ground, so the elevation will be 0, so it doesn't have any potential energy. So basically, just we need to balance these energy forms. So we say that the potential energy this body has initially equal the kinetic energy this object has finally. So we have m g h, this one equivalent to half mv squared. We have the same object, so we have the same mass. Okay, then we have h, the height we have, this is 50 feet. We have g, gravity, we have two values, 9.8 meter per second square, which is equivalent 32.174 feet per second square. So if you will use the height, or you will express the height with 50 feet. So which value of g you will use? Will you use 9.8 or 32? 32. We need to make consistency of the units. Okay, so now use these numbers, substitute them. So we have 32.174 times 50. This will be equivalent to half v squared. So we just substitute here, and we will have the velocity as 56.7 feet per second, and this is what we need to calculate. So this will be the velocity this object has just before it hits the ground. Clear? Any questions? Okay. So this is what we have about about kinetic and potential energy. The last form of the static forms of energy, which is new, is the internal energy. So the internal energy, this represents the energy stored by the molecules. If you remember, when we start talking about the internal energy, we said we have kinetic, potential. This is macroscopic. It focuses on the whole object. But if we start focusing about the molecules, then we are measuring or calculating the internal energy. So internal energy, this is a microscopic type of energy because it focuses on the amount of energy stored by the molecules we have. Why molecules have this type of energy? Because molecules always in random motion. We have molecules can have translational motion, they move from one place to another place, rotational motion, or even vibrational motion. Because molecules always in motion, so this is why these molecules have internal energy. Internal energy is affected by several factors, including temperature, pressure, volume, the forces between the molecules themselves. So all of these forces can affect the value of the internal energy we have. But we cannot measure the value of the internal energy. What we are doing is we are measuring internal energy relative to a reference. So this is why sometimes you can have negative value of the internal energy. So this doesn't mean that the molecules are not moving. No, the molecules are moving, but this value is negative compared to the reference you have. Let's take an example for this. So we know that, as we said, internal energy affected by temperature, right? So do you think if we are increasing the temperature, what will happen to the internal energy? Increase or decrease? Increase, because the motion of the molecules increase. So let's say I need to find internal energy, like this is temperature, and internal energy. I need to calculate internal energy at 20 degrees Celsius. Let's call it U1. 50 degrees Celsius for a substance. Let's call this U2. 70 degrees Celsius and call this U3. So we know that U3 is more than U2 is more than U1. Clear? Okay. Let's select this condition to be my reference. So now, this is my reference. Okay. So now you are calculating U2 compared to U1, and we know that U2 is more than U1. So the internal energy value you are calculating will be positive, because what you are measuring is more than your reference. If you want to calculate or express the internal energy at this condition, 70 degrees Celsius, you want to express U3, you are expressing U3 compared to U1. And we know that U3 is more than the U1, so the internal energy, it will be positive. Make sense? And let's say if someone select this case to be the reference, not this one. Now this is my reference, U3 or 70 degrees Celsius, this is my reference. What will be the internal energy at 50 degrees Celsius? So does it make sense to be positive? If it's positive that you are saying the internal energy at 50 is more than the internal energy at 70, and doesn't make sense? No. So this is why if you are measuring internal energy at 50 compared to 70, the value will be negative. So the negative means the internal energy at this conditions less than your reference. Okay? So this is only the sign means. Positive sign, it means the internal energy is more than whatever reference you select. Negative internal energy means this value of the internal energy just less than whatever internal energy at your reference state. So it's sometimes you will see this happen, that the internal energy can be negative. Okay? So now if we focus on the total energy of the system, so we have that the static forms of energy stored in the system. So any system have three types of energy stored in it: kinetic energy, potential energy, internal energy. And if you need to calculate the total energy of the system, you should sum all of these three types. So what is the value of internal energy plus kinetic energy plus potential energy? This is called the total energy that we have of the system. Okay? Because it's a summation of everything, all the static forms of energy. This type of energy is extensive property. And again, you remember, do we like to deal with extensive or intensive properties? Intensive, because intensive property not function of the size of the system we have. So how I can convert extensive to intensive property? Divide by mass or divide by mole. So we can do any one of them. So if we have the total amount of energy divide by mass, then we have specific total amount of energy. It has E hat, or we also express it as E small. So just different textbooks use these two concepts. So this will be the specific internal energy plus half V squared plus GH. Okay? So again, if we have system have kinetic, potential, internal, do you think all of these three types contribute with the same or have the same contribution to the energy of the system or not? So let's see which one contributes a lot. If we have 1 kilogram of liquid water at 20 degrees Celsius moving at 50 meters per second, and we inside a pipe, and this pipe is 20 meters above the ground. So again, we have here water. The temperature is low. 20 degrees Celsius is relatively low, right? But this is moving at 50 meters per second. We have very high velocity. 50 meters per second is a lot. This is for sure a turbulence. Okay? We have randomness in the flow. And 20 meters above the ground, this is high elevation as well. Just if you can see these numbers. So the temperature is low. You can expect that, okay, so since internal energy affected by temperature is low, so the value of the internal energy will be low value. Make sense? Then we have very high speed, so the kinetic energy will be huge. The elevation is huge, so also the potential energy will be significant. But if we calculate these three values, then we will find that even if you are at 20 degrees Celsius, the value of the internal energy is 83.9 kilojoules. You are moving at 50 meters per second, very high velocity, so the kinetic energy is 1.25 kilojoules. You are at 20 meters above the ground, which is a high elevation, but at the same time the potential energy is 0.196 kilojoules. So this means even if the temperature is very small, the velocity is very high, the elevation is very huge or very high elevation, but the amount of the internal energy compared to the kinetic and potential is what? It's very huge. So almost more than 98% of the energy stored in the system, it comes from which one of them? Internal or potential or kinetic? Internal energy. So this is why we can have the kinetic and potential energy. Usually in the problems, we are neglect them compared to the internal energy. Okay? Because in the problems, you cannot achieve 50 meters per second. For sure, you will use lower velocities. At the elevation, it doesn't make sense to have a pipe, and this pipe is 20 meters above the ground, for example. Always the pipe is 1 meter, 2 meters above the ground. So even if you work at real conditions, the kinetic velocity will be less than this value. The potential energy, kinetic energy and potential energy will be less than this value. So their computer is reducing. So this is why in the problems, in most of the problems, or even the derivations, when we are expressing the total energy of the system, we are using only what? Internal energy. Okay? So usually we neglect kinetic energy, we neglect potential energy compared to the internal energy. Is it clear? Any questions? Questions? Okay. So again, we have all of these forms of energy, static and dynamic together. Which one of them can exist in open system? Which one of them can exist in closed system? So you can also check this one. Just a summary of the everything we have covered in terms of the forms of energy and how this related to types of the system, open or closed systems. Okay, so just can give you like guidance of if you have an open system, what is the forms of energy that you are expecting to calculate or required from you to calculate, or what will be the same case for open systems. The second part is the fundamental laws of thermodynamics. We will cover this topic in future chapters, but just very quick hint about this, we have 4 laws of thermodynamics. Okay, most important one, or the ones that we will talk about, is the first and second law of thermodynamics. We have whole chapter discussing first law of thermodynamics, another whole chapter focusing on the second law of thermodynamics. But just to give you the idea, we have the first law is called the zero law. And this zero law just gives you the fundamentals of defining temperature. This was the importance of this one. So how we have temperature, how we can define temperature, how we can calculate the temperature. This comes from the definition of the zero law of thermodynamics. This is why most of the slides we have covered so far, if you remember, we mentioned the name of Lord Kelvin. Okay, he has significant contribution to thermodynamics, and even one of the temperature units is named after his name. Okay, so he had this contribution of this one. Then first law of thermodynamics, this is the conservation of energy. We have applied it in the previous example when we said we have potential energy, system is losing potential energy, but the amount of energy this system is losing is converted into what? Into kinetic energy. So if the energy is losing in one form, it will appear in another one. Second law of thermodynamics, this one is related to the entropy, and this one will give you an idea about the direction of the process. So if you have ice, for example, and put your ice on the table and leave it for a few hours, what will happen to this ice? It will melt, right? But if you have water and you leave it for years, when you come back, are you expecting to have it as ice, or will it stay as it is?
Wow.
It will stay liquid. So why this happening? The answer is from the second law of thermodynamics. So the second law of thermodynamics is tells you why any process happen in one direction and not in another one. Okay, so we will discuss it in upcoming chapters. The last one is the absolute zero, and how the system will behave at absolute zero. Absolute zero, which is 0 Kelvin. Okay, which is negative 273 degrees Celsius. So this law is focusing about this one. Okay, how the system will behave at this absolute zero. Okay, so this is just a quick idea about each one of them. And as I said, the first and second law we will discuss it in detail in upcoming lectures. The last point we have in this chapter, so now we have an idea about thermodynamics, how this one is related to energy. We understand that this one is somehow related to sustainability. We have some rules in the energy sector that we need to apply thermodynamics in this one. So if we understand all of these things, so what thermodynamics can help you as an engineer? Basically, thermodynamics help you in 4 things. It can help you to understand the basic concept, any basic concept that consider or contain energy transfer. Any process that has energy transfer, you need thermodynamics to understand the mechanism of this process, what is happening in this process. Then it will help you to analyze this process. How we can analyze the performance of this process. So the thermodynamic principles we are studying, you should know how to apply them to analyze the process. How you can calculate the efficiency of the process. How you can calculate other thing called coefficient of performance. How you can improve the performance or the efficiency of this process. Then we need to design a process. So again, thermodynamic laws, this one are helping you to design efficient systems. So at the end, I need to have an efficient system. An efficient system means to give you the same output, the same product with the minimum amount of energy. Okay? And finally, thermodynamics help you in operation of these systems. How you can control your process in order to ensure that you have the optimal performance, the best temperature, that if you operate this the unit or the reactor or whatever unit we have at this temperature, it gives you the maximum yield. What is the best pressure that you have? What is the optimum flow rates for the process? That if you operate at these flow rates, then you are ensuring that you are obtaining at the maximum amount of yield that we can have. Clear? Questions? Okay. So this is everything. This is a summary of everything we have discussed in this chapter. Okay. Just when you're studying, keep this mind map in your mind. So this chapter just have 5 topics we covered. Again, we started with units and dimensions. So here we have discussed what is meant by the system of units. We have SI system, we have American system, how we can convert the units from one unit to another one, and other problems we try to give examples of these things. And then the idea of dimensional homogeneity. If you have an equation, each additive term in both sides of the equation must have the same units. Then we give an idea about the energy, what are the types or forms of energy, what are the sectors of energy, and the differences between them. Then we start talking about thermodynamics. We start with a quick history of thermodynamics, what is meant by thermodynamics, application of thermodynamics in engineering, and the laws of thermodynamics, zero law, first law, second, and third law. Then the 2 important parts in this chapter are these 2 points. These are the core we have, plus the conversion and dimensional homogeneity. These are very important. So the basic concepts and terminology, so we should know what is meant by system, different types of system, or the difference between open, closed, isolated system. State and properties, what is the difference between extensive, intensive property. State function, path function, so you should know the differences between them. Process and cycles. Cycles, as if you remember, special case of process if the initial and final state are the same. What is meant by steady state? The value of your variable or property is constant with time. Equilibrium is related to the driving force. We have thermal equilibrium, mechanical, chemical equilibrium, and phase equilibrium. Then we discuss forms of energy. We say we have 2 types: static forms of energy, dynamic forms of energy. Static forms of energy are internal, kinetic, potential. Dynamic forms of energy, heat and warmth. Okay? Clear? Any questions? Anything you have in your mind regarding this chapter? Okay. Good. So this is everything we have regarding this chapter.